Hello and welcome. Today we're going to be talking about matrix algebra versus real number algebra. And this is our introduction to matrix algebra. We're going to really take a bird's eye view approach of it and really understand it in terms of something that we're more familiar with, which is real number algebra. And I think a lot of students, when they're first learning matrix algebra, what they find is a lot of the difficulties or challenges they have is that they need to maybe see real number algebra from a bit more of a basic or high-level approach. And once you understand real number algebra from that high-level approach, matrix algebra fits right into place. We know where to put it, and we know how to understand it and interpret it because we've seen the same sort of features show up in real number algebra. So let's talk about matrices first. So matrices that we can talk about them. Well, I was always going to use capitals for matrices. So things like capital A, capital B, and capital C, and they always be matrices. Okay, and so in the most basic sense, they are basically grids or arrays of real numbers. Okay, so one could also ask, well, what about complex numbers? And you certainly could do a lot of things with complex numbers as well, but for right now, we'll restrict ourselves to real numbers to keep it simple. And so, of course, you might write A. This is an example. A is equal to a grid, 1, 2, 3, 4. Okay, so that's a grid, and we call this a 2 by 2 matrix, because it has 2 rows and 2 columns, so we can say these are the columns. Okay, so there's 1 and 2 columns. And then here, of course, there are 2 rows. And so that's how we always talk about a matrix. And so what we really want to say is a matrix always has a dimension. So in particular, of course, a matrix can be n by m, and that means it has n rows and m columns. Okay, so how do we always keep track of the order? And the thing we always like to do is the mnemonic. The mnemonic is always, what's your favorite cola? So, of course, it always goes rows first and then columns. So your favorite cola that you always answer is RC. So it's a Royal Crown Cola, if you remember that or anything. But RC Cola, and you always remember R is rows, and then C is columns. And that's how you always keep track of what a dimension is. Okay. So there are different types of matrices. It depends on the number of columns and rows it has. So of course here's another example. Maybe we'll do a 2 by 3 example here, and that's a matrix. We can say 1, 2, 3, 4, 5, 6, like that. Okay, so that would be a different matrix than say here, which is a 2 by 2. And sometimes people will actually put the dimension underneath the matrix, and that's just a helpful marking if you need it, if it's not understood by context, to know what the dimension of a matrix is. Okay, so of course another thing. So what's your favorite cola? RC. Well, RC is hardly anyone's favorite cola, so that's what makes it a bit funny. But that's a good way to remember. Row column. It's always row column. So again, row is this way, up and down. That's row, and then columns are all along here. So here would be column 1. There would be column 2. And this would be column 3 right there. So that helps you kind of understand and organize this and understand the structure of a matrix. Okay, another notation. So we need to be able to understand A in terms of its entries. So these are, of course, all the entries. So all those things are entries, all these numbers. So A we can actually write as Aij, where of course that is the RC column written there, and then AIJ is the entry in row I and column J. Okay, and that's just a nice notation we'll use if we want to know what kind of things are inside of A. We can say that they're lowercase a's, and we're going to use lowercases for all real numbers and capitals again for all matrices. Okay, so that's the basic definition of a matrix. That's how we write it. We always put those square brackets around it. Sometimes you'll see in practice round brackets as well. Either one's fine. I'll always use square though. Okay, so the question now is we're not just talking about what matrices are, we're talking about matrix algebra. And what we really need to do is go back a bit and actually talk about, well, what is, if we want to know what matrix algebra is, we have to actually understand what again was real number algebra. And what we're going to find out actually is that although we're very comfortable doing algebra with real numbers at this point in our mathematical education, we'll find out that maybe we need to actually revisit it and remember, or maybe talk about it in maybe a little bit more sophisticated way. And that's going to really help us when we do our matrix algebra. Because one thing about real numbers, they are actually matrices. They are one by one matrices. Okay, so in a sense, we know what they are. What we've already dealt with matrices before. They are real numbers are one by one matrices. Obviously, when you get larger dimensions for your matrix, things can change. But let's now talk about what real numbers are, and what this also begs the questions. Okay, what's real number algebra? What's algebra? So what is algebra? So at base, algebra is a set of stuff. So one, it's a set of stuff, and that could be numbers. Okay, and then two, it's a set of binary operations. Okay, you know what these binary operations are. We know them as plus, minus, I'm going to use the dot for multiply, and then also divide. Okay, so we've seen all those operations, and the reason they're binary is because it always takes two inputs, or two inputs. So for instance, right, if I have 2 plus 3, see there are two things, and I'm adding them together. So plus actually accepts two inputs, and it gives out one output, so it's 5. Okay, right, and of course there's 2 times 3, and that's 6. That's always nice and well and good. So really, I like to think of algebra as actually a plus and a multiply, and the subtraction and divide are actually kind of partner operations of plus and multiply, respectively. So we'll really focus on plus and multiply here. Okay, so one thing that's really nice about algebra, okay, so we have, so algebra is a set of binary numbers, but one nice thing, so real numbers, so this is a key feature of real number algebra, is that the ability to undo an operation. Okay, so the ability to undo an operation. So for instance, if I have 2 plus 3 equals 5, and let's say, so what I've really done here is, let's say if I want to undo the plus 3. So what of course I do is, you know what to do, is you're going to now subtract 3 to undo. So subtract 3 is the undo. So if I have 5, then I add minus 3 I get back out, get back to where I came from. So that I undone, if you will, undone the plus 3 to get back 2. Okay, and so we also know that we can also do, and one key fact about this is this can be done for any number. You take two numbers, add them together, you can always subtract off one of the numbers and get back to where you started. Okay, and that's really important. And so actually we give this a name. So if I have A is some real number, and I'll give it this symbol, A is in the set of real numbers, and that epsilon means in, okay? If A is in the set of real numbers, then there exists a minus A such that A plus minus A is equal to 0. So this has really nice properties. So we actually call this, minus A is the additive inverse. And 0 is what we call the additive identity. Okay, so for every A, I can always find a minus A such that when I add them together, I get 0. I get nothing. Okay, so that's really nice. So we always have these additive inverses and an additive identity. And those are really important objects in our algebra. Okay, so let's now, so we have this additive inverse and additive identity. What about multiplication? So multiplication, it also has the same features. All right, so let's talk about that. So multiplication, of course, we have A times B, and that's going to equal C. So, give an example, of course, 2 times 3 is equal to 6. And the question now I want to undo the multiply by 3. So what, of course, you do is you divide by 3. So of course, if I have 6, I have 6, and I divide by 3, I get back out 2. Okay, that makes pretty good sense. Or rather, another way to say the same thing is I actually multiply by 1/3. Okay, so if I take 6 and I multiply it by 1/3, I get back out 2. So it's the same thing, the idea that I've just changed how I thought about it. So what we say now is that 3 has a multiplicative inverse. Multiplicative inverse 1/3. We can also say this is 3 to the negative 1. All right. In fact, any non-zero number has a multiplicative inverse, mi. Okay, and of course, if I have A, then there's its pair, its inverse pair, which I call A to the negative 1. Okay, and that's true for any number except for 0, and that's the big thing. 0, the additive identity, has no inverse. And that's really interesting here, the idea that there's only one number that doesn't have an inverse. Every other number has an inverse. So of course, 1/2, that has an inverse of 2. And that's very important, the idea that actually an inverse of an inverse is the number itself again. So the inverses are actually pairs of inverses. They're both inverses mutually invert. They mutually invert each other. Of course, when you times a by a to the negative 1, you get back out 1. And 1 is what they call the multiplicative identity. All right, and so the thing about 1 is if I take 1, I multiply it by any number times b, I get back out b again. So there's no change. So let's summarize this. So we have a bunch of features. We have inverses. So we have inverses. So if we have a, it has two different types of inverses. It has minus a and also a to the negative 1. Okay, and that's provided a is not equal to 0. For this one, okay? And then we have identities. We have 0, 0 plus a, you get back out a, okay? Of course, 1 times a, you get back out a again. Okay, very nice. And why these work so well is, see, if you have an equation, of course you have a times x is equal to b. What I can do then, of course, is multiply both sides of the equation by a inverse, and I get x is equal to a inverse times b. And that is a nice result in order to solve for x. And the idea is that you're undoing the operation of a times x in order to uncover x again. And that was the important aspect of undoing or inverting, was that an algebra that has a way to undo an operation can allow you to solve equations. Okay, and so the question then is, and one nice thing about this, so I'll talk about this in one more sense. So also real numbers has, the standard rules. Okay, so real number algebra has a standard rules. The first rule, of course, is associativity. So we know that a plus b plus c is equal to a plus b plus c. Okay, and likewise for multiplication, a times b times c is the same thing as ab times c. Okay, so that's associativity. And 2, we also have commutativity. So commutativity is simply the idea that a plus b is equal to b plus a, that order doesn't matter, and also ab is equal to ba. Right, and finally distributivity, that's how the two operations interact. And that is that a times b plus c is equal to ab plus ac. Okay. Those three things together, I'm sure you've seen all these rules before, but now again, with all these together, if I want to solve for x, and if I have a times x is equal to b, and I know what a and b are, and then provided a is not equal to 0, then a inverse times ax, and what I can do is actually add the inverse of b, the additive inverses of b over. I get 0, and then I can multiply both sides of the equation here, and I get a inverse times a times x minus, use the distributive property, a inverse times minus b, and that gets us a 0 over there, and because 0 always multiplies by anything to get 0, it's the only number that doesn't have an inverse. You can't undo that operation. Once you multiply by 0, you can't undo it. And that's the whole idea behind 0 not having an inverse. All right, and then of course I can use the associative property here. And then move this back over. And then finally, this, of course, always multiplies to be the additive or the multiplicative inverse. So we get x is equal to a inverse times b. So in order to solve this equation, we used every single one of these laws, and we used the notions of inverses and identities in order to understand how to do algebra. Okay, so the question then is, now that we have a good background in algebra, can we do the same thing with matrix algebra? So this video, I don't want to go overboard in doing everything all at once, but rather I just want to talk about how are things different. So of course we have A, so I'm going to talk about addition. So addition, if I have A is equal to Aij, and if I have the matrix B, which is going to be Bij, we want it to work exactly the way real numbers work. We want A plus B to be equal to the entries Aij plus Bij. And the idea here is each entry sums. Okay, so that's fairly straightforward. I can give you an example over here. If I have 1, 2, 3, 4, and if I have plus, 5, 6, 7, 8, then that's going to equal 6. 2 is going to add to 8, or 2 is going to add to 6, and we're going to get 8. 3 is going to add to 7, we're going to get 10, and then 4 is going to add to 8, we're going to get 12. Okay, that's very straightforward to do that example there. And of course, this is associative and commutative. Okay, and that's because A plus B plus C is going to be equal to A plus B. Plus C if we had another matrix there, C. And also A plus B is equal to B plus A. Oops. Like that. So we have the associative and commutative properties. They all work just fine. Okay, but there's one big catch here, okay? So A and B must have same dimension. Okay. So the next question then is, what about multiplication? So multiplication turns out to be really, it's here that it differs greatly with real numbers. Okay, so first of all, A times B does not always equal B times A. Okay, A times B is only, so that's the first, so we don't have, so it's non-commutative. And AB may not be defined depending on dimension. So that is another thing. Before, we could always multiply any two real numbers by each other, and it always worked. But it turns out here that we need the dimensions to be just right in order for A times B to be defined. And even when it is defined, they may not commute. So let's actually go through that. So what we want out of matrix multiplication is to be continuous or consistent with linear systems. All right, so for instance, if I have 2x plus 3y minus x plus 2y is equal to 1, and that's equal to 3, I want to be able to write this as a matrix 2, 3, negative 1, 2. And then I'm going to have, so that'll be my matrix A, right? And then I also have this new matrix that I'm going to call a vector, and it's going to be, it's going to be equal to x comma y. And I put that little arrow over it to indicate that this is actually a 2 by 1 matrix. Okay, and then finally B is going to be 1, 3 in this case. All right, so how does matrix multiplication work? We can clearly see that it's the 2 there that multiplies by the x. We see a 2 there, and it multiplies by the x. And then the 3 multiplies by the y, right? And that equals 1 over there. So something about how we have a row here and a column here, and when you multiply them together, you add up the result and you get 1. Likewise, down here I see that other row, and it's almost as if the column here tips over on its side and multiplies by the elements of each row, and that's what creates the each row. So we need a way to define this. So in general, we require the number of rows of x to be the same as columns of A. All right, and so also in general, if I have A and B, what I need actually is, if this is n by m, I require that, again, it's the number of rows in B has to be the same as the number of columns. So what we see is exists, AB exists if these are the same down there. So these two have to be the same. These can be different. All right, and AB then is equal to C, and it turns out that C will be n by P, and that'll be the outer two. Right, so it's going to have the number of rows as A and the number of columns as of B. And that's the same thing over here. Do you see that this is a 2 by 2 matrix here? This is a 2 by 1 matrix, so A times X, 2 by 2, and X is going to be 2 by 1. We see the result then, we'll have on the other side what B is. That's going to be a 2 by 1. 2 by 1, because we bring those together like that. Okay, so hopefully that gets you some idea of what matrix multiplication is. Now I'm going to actually write it down and define it in a really crisp way. So in general, if I have an A that's n by n, and then I have a B that's m by p, AB is going to be equal to C, which is going to be Cij, where Cij, and this is a pretty complicated thing to write, but it's actually going to be the sum across the columns of A. So it's going to be Aij, and we're going to sum across J is equal to 1 all the way to M, and it's going to be B J K. So actually I'm going to write that as that right there is going to be K. So Cik. Okay, like that. And that is going to be the definition then of matrix multiplication for each entry. Now that is going to take a little while to digest. In the next video I write, we're going to figure out a better way of doing maybe a little bit more simpler way to understand matrix multiplication. For right now, All I would want to say is that it needs to be consistent with what we know about linear systems and how we express them in terms of matrices. Okay, and the other thing, of course, we want to know is the one thing we want to keep in mind is that matrix algebra multiplication does not behave in the same way, in the same clean way as as multiplication does in real numbers. And finally, what I'll write down here, the last fact, multiplicative inverses of A may not exist. Okay, so we'll learn more about that in the next videos, but I hope that gives you a high-level understanding of some of the issues and questions involved in matrix algebra and how they relate to real numbers. So thank you very much.